different ways of preparing old favourites such as steak and kidney pie and ice cream. That's quite a mixture, soon on BBC1. Well, back here on Daytime on 2, we continue with more maths help.
Problem. 1, 3, 6, 10. Write down A, the next number in this sequence, B, the 15th number, C, the 23rd number.
There's the problem then. First bit's not too bad, but to calculate the 15th number you have to do an awful lot of arithmetic. The 23rd number's even worse. It must be an easy way, it usually is. And this time, the easy way involves a concept that's central to all of mathematics. And that's the use of symbols to represent numbers. So let's first of all step back and think about the use of symbols to analyse a problem. Now, ladies and gentlemen, I want you to concentrate carefully and do everything I tell you. First of all, think of a number between 1 and 10. Now, add 3. Multiply your answer by 2. Add 8. Now divide by 2. And subtract the number you first thought of. And what you're left with is 7. Well, that's very impressive. But how was it that he knew that whatever number you thought of, as long as you did the arithmetic right, you were going to end up with the number 7? I suppose that if you played the sequence over and over again, then eventually you might get some idea as to why it was he could always predict that you'd end with the number 7. But it's a very complex set of arguments in words. So what we're going to do is to replace the words by symbols and use symbols to analyse the problem. First then, let's look at the list of instructions that he gave. First of all, think of a number between 1 and 10. Now, add 3. Multiply your answer by 2. Add 8. Now divide by 2. And subtract the number you first thought of. And what you're left with is 7. But in order to use this information mathematically, we must write it using mathematical symbols like this. Think of a number, add 3, multiply by 2, add 8, divide by 2, take away the number you first thought of. And so our final expression, that's what the magician told us, in mathematical terms, is this. It's a half times twice the number plus 3 plus 8 minus the number you first thought of. Well, that looks a lot better. We've got a lot of symbols here now, and we've written the list of instructions in one go. But the only thing that looks a bit uneasy is that word number. You see, we can't actually write a number there. We can't write 2 or 3 or 7 because I don't know which number you were thinking of. But nevertheless, the word number looks clumsy amidst all those nice symbols. So let's replace that word by a symbol itself. Let's use the symbol n. And then we get this. We get a half of twice n plus 3 plus 8 minus n. You may think that's no better than a whole list of instructions. You may think that looks a bit off-putting. But it is a lot neater, and it's a lot more precise. But there's more to it than that. Here's the set of instructions written in symbols. And what I'm going to do is to replace that by a simpler form. And I'll see how far I can go and how simple I can get it. First of all, I'm going to look at this little bit in the brackets here. I can replace the twice n plus 3 by 2n, that's 2 times n, plus 2 times 3, that's 6. And then the whole expression must be equal to half, I haven't done anything to that, times 2n plus 6, plus 8, haven't touched that yet, minus the n. Now then, what can I do now? Can I simplify it further? Can I find another expression which is equal to that but simpler? Well, I can put these two together. I can replace the 6 and the 8 by 14. Then I get 2n plus 14 inside the square brackets. I have to multiply by a half or divide by 2 and subtract n. Now I can go a bit further still, because now I can get rid of the square brackets. I can multiply each of these bits by a half. I can replace it by a yet simpler expression. A half of 2n is n. A half of 14 is 7. And minus n. Now what have I got? I've got a number, add 7, take away the same number. So that must be exactly the same as 7. And that's how you did it. Whatever number you thought of up here, whatever the value of n is, what I've just shown is that that expression always equals 7. And each of these expressions can be expressed as a set of verbal instructions. But the point is that as you move down, they get simpler and simpler. The magician could have given us any one of these set of instructions. He could have said, think of the number 7. The number you're thinking of is 7. But that wouldn't have been very impressive. He could have been a bit cleverer. He could have said, think of a number, add 7, take away the number you first thought of, and the number you've got now is 7. But even that's not very clever. All he did was to move up in levels of complication until he got an expression like this, which was complicated enough so that you couldn't see immediately what the answer was, and so he could mystify you. So he wasn't really a mind reader, he was just a simple mathematician. Back to our problem. Remember, we were given a sequence of numbers, 1, 3, 6, 10, and so on, and asked to find the next number in the sequence, the 15th number, and the 23rd number. These numbers are called triangular numbers because they can be represented as triangles of dots. 1, 3, 6, 10, and so on. Now, we could work out the triangular numbers just by adding a row at a time until we got to the 15th and the 23rd. But that would be inconvenient and time-consuming, and what's more, if you asked to find some other triangular number, you'd have to start all over again. What we want to do is to be able to talk in general terms about any triangular number in the sequence. We want to use symbols to get an expression for any term in this sequence. The first term is 1. The second is 3. The third is 6. The fourth term is 10. And so the nth term is... and that's the problem. How many dots are there in the nth pattern? We've used the symbol n to stand for a general position in the sequence, and so the number of dots in the general position must depend on n. Now, to get a formula involving n for the number of dots in the nth position, we're going to use a bright idea that occurred to somebody once. Now, don't worry if you think, oh, I'd never have thought of that idea, because I didn't think of it either. It's just a brainwave that somebody once had to crack the problem. Suppose we do this to the nth triangular number. We can double up the dots with crosses and so turn the triangles into rectangles, like this. In each case, we get twice as many crosses as dots. But it's much easier to calculate how many crosses there are. The first rectangle has 1 row and 2 columns. And 1 times 2 is 2. The second has 2 rows and 3 columns, and 2 times 3 is 6. And the third has 3 rows and 4 columns. 3 times 4 is 12. Can you see the pattern? In each case, there's the same number of rows as its position and 1 extra column. So let's think about the nth rectangle. We don't know anything about n, except that it's some number. But we do know that the nth rectangle must have n rows and n plus 1 columns. And that's important, because we can now manipulate the symbols to solve the problem. Okay, how many crosses are there in this rectangle? Obviously n times n plus 1. So clearly, the number of dots in the nth triangle must be n times n plus 1 over 2. Remember, the number of dots is half the number of crosses. And we've done it. This formula tells us the nth triangular number. So the 15th must be 15 times 16 over 2, which is 120. And the 23rd must be 23 times 24 over 2, which is 276. So using symbols, we've cracked a very difficult and time-consuming problem. In each case, we ended up with a formula and actually had rather a similar look about them. Even though one came from calculating dots in a sequence of triangular patterns, highly mathematical, and the other one was really a bit of fun and a number game. But in each case, we were able to manipulate symbols using straightforward arithmetic processes. Mathematics is about symbols, and that puts a lot of people off the subject. But you shouldn't be frightened, because ordinary words are symbols, and if you couldn't read, then you'd be frightened by a page in a newspaper. And you'll find that once you learn to read mathematical symbols and manipulate them, you have in your hands one of the most central tools of mathematics.